What am I talking about? It's a little bit more down in the implementation than some of the previous talks. So hopefully that'll appeal to some of you. Yeah, what am I talking about? Making the world a better place through Paxos algorithms. No, really. Does anyone watch Silicon Valley? Yeah, okay. That's where that still is from. This is a quote from many websites, but I saw this. I didn't want to show the real website, but this was on a website, people that turn over like £2 million a day, something like that. And it said, the server is experiencing issues. Really? You have one server. Well, that's great. And in fact, it's a great simplifying feature of your system. If you have exactly one server with everything running in it, then that's really going to make a lot of things easier. However, I wanted to put this. We run more than one thing a lot of the time, and I wanted to put that thought out there. Any system with more than one container is a distributed system. The world is changing, and I'll come back to that thought. What am I really talking about? Reliable systems. So we don't want the entire thing to go down when one piece fails. So we run more than one of them. And now you need to get the state in multiple places. And you don't want the state to be out of sync. So you need to replicate the state somehow. And that's hard. This is a list. This is the 8 fallacies of distributed computing. This is a list written down by Bill Joy. Everyone has to quote Bill Joy, right? And some other people. 20 years ago, they wrote these down. These are things that people may believe about distributed systems, but which turn out not to be true, because the network is not reliable all the time. Latency is not zero. Bandwidth is not infinite, and many, many more. So, I'm adding something we also need to remember, which is that hosts. So the fallacy might be that hosts stay up forever. They don't, right? Hosts can crash, or your cloud provider can reboot them for you to improve service. So, what do we do about this? Well, okay, there's a reminder from what I'm supposed to be saying. So one great choice a lot of people do is they pull a component off the shelf that is designed for managing distributed state. And there's a number of these, etcd, console, zookeeper. There's a number of these components, and they're great. They keep your state consistent for the most part, and you plug them in. They are a bit complicated internally. Some of them more complicated than others to manage. But fundamentally, the technique they use, called a consensus algorithm, and that's Paxos is the name of a consensus algorithm. So what do they have to deal with? They deal with lost messages. You sent something, it just didn't arrive. They deal with delayed messages. Things arriving in the wrong order, hosts crashing. So an example of the worst kind of thing that can happen is you made an update, and just after you made the update, the host crashed. So now when you're trying to build one of these things, you have to think about, okay, so what do I do if the update did make it off the machine, and what do I do if the update didn't make it off the machine, but it is on the disk? So when this guy comes back up again, he thinks that update is good. And these algorithms, like Paxos, they cover all those cases. They're a great thing. They're mathematically proved because it's basically impossible to test for all these conditions. So that's a great way to do stuff. let's look at the cost of doing consensus. So I have this little animation here, which is kind of cute. And the basic way that you make sure your systems have a consensus is by sending a lot of messages over the network. And fundamentally by making sure that you have communicated each update to more than half of the machines in your cluster. And when you get more than half, that means that nobody can be under a misapprehension. Nobody can subsequently move on in the system. You get what's called a network partition, where half the hosts can't talk to some other half of the hosts. That you can never get into a confused state and be unable to move forward. The flip side of that attribute is if you are on a side of a partition, if your network's not working temporarily, then nothing can move forward. You are halted. If you're using one of these tools, if you're using this technique of consensus algorithms, if you're in a network partition which does not have a majority, you cannot move forward, you are halted. So that is a significant issue for availability if you want your system to be up and taking money or whatever. And sending all these messages around has a certain performance cost as well. I ran a little benchmark. This is the test setup. I was running 3 copies of etcd, and I just thought I'd throw this picture up there because Weave is the company I work for, Weaveworks. This picture generated by Weave Scope, that's one of our products, and it just automatically drew the picture. You just point it at your host, and it figures out what's running and draws a picture of what's running, and you can drill into the metrics and so on. So that's kind of cute. One of our other components called Weave DNS. It's used for service discovery, and I ran a benchmarking thing called DNS Perf, which is reasonably popular for testing these things, and I benchmarked it against a thing called SkyDNS, which is also very popular. Both Weave DNS and SkyDNS, by the way, use the library from Miek, who's talking later, if he can get his laptop to work. Hey, there he is. So big shout out to Miek for the fundamental DNS parsing and handling. But what I really wanted to draw attention to is when I put etcd into what's called strong consistency mode, the performance drops off by like a 20th, or well, to a 20th. When you run consensus algorithms, they cost a certain amount in performance. That might be okay. You know, there's 500 queries per second or something like that. Is fine for a lot of applications. But I just want to stress the impact that a consensus algorithm will have when you're running it. Okay, so engineering is all about picking trade-offs. It's one of my mottos. I sometimes call myself an engineer. So, you know, is there another trade-off? Is there another way to do this? Just come fill in a bit more of the background. Why am I talking about this? Basically, because we've been using an alternative technique that I'm about to talk about. Why do we want an alternative technique? We have various services in our suite of products. Weave is connect, observe, and control Docker containers. So connecting your containers up, figuring out what they're doing, and controlling the way they run. So a couple of things within that suite: service discovery, which I've mentioned, and IP address allocation. When we connect up all the containers, they need to have a unique IP across the entire cluster. But we don't want this attribute that the half your network halts if you have a network partition. And we're targeting people running, you know, on your laptop. So you run maybe some of your system on your laptop and some of it on the cloud. When you fold up your laptop, we don't want the rest of the system to halt. We want the system to carry on running as pieces come and go. So so that's the background. Why were we interested in this kind of question? So the Paxos, a Raft, which is another kind of consensus algorithm. So these are all algorithms, and I borrowed Vert's book title, Algorithms Plus Data Structures, because I'm going to talk about a data structure-centric way of approaching the same problem. How important is it that every single node on your network knows the same data? In the case of services discovery, the basic problem is I want to find a service and I've run 3 copies of Redis or something like that. So I have a list that has those 3 things in it. That's the basic problem. If you think about it, the minute you pick one of those 3 servers, it could crash right then. And there's no transaction you can run that keeps you consistent between whether that service is running and whether it's in your list. Right? It's just fundamentally impossible. There is no technology that can make that work. So actually, there's no point in keeping your list globally consistent and fully up to date and absolutely spanking new if that is your problem. And on the big wide internet, DNS is not fully consistent. So you can reframe the problem. IP allocation, most of the time, you don't care what somebody else is doing with their IP addresses. You can do local allocations. What we do in Weave is we rebalance from time to time, and we need to talk to other machines. But most of the time, it's completely local. And we don't need consistency. We don't need immediate consistency. We don't need consensus. We aim for eventual consistency. Let's take a look at how that works, how that looks. What I'm really talking about is a thing called a convergent replicated data type, a CRDT. And this is a type of data structure. The generic idea is you can make updates independently, and then you can merge those updates together. And the requirement of the merge is, that's big funny words there, commutative, associative, and idempotent. Basically what it means is if you get an update out of order, it doesn't matter. You can merge them in any order. If you get multiple updates, it doesn't matter how you group them. If you get the same update again, it doesn't matter. You can that's a requirement of a CRDT, is that you have a merge function that has these properties. And then you can start using it. So in this example, the data structure is a set. Merge function is to union the sets. So if we start with A, and in one place we add B, and in another place we add C, we can merge the 2 and we get ABC. Fundamentally, it is that simple. A lot of people get very hung up on the way these things are described. They're very often using a lot of jargon, and they're using the upside down V and the backwards E, and does anyone else have that problem? Yeah, so really, the fundamental ideas of these things are pretty simple. That's one of the things I wanted to get across. So how does this apply? That was, CRDTs are awesome. How does this apply to some of the things I've been talking about? So we implement DNS pretty much as a set. It's the set of things that are running. The same thing could be running in multiple containers on multiple hosts, so we need to add those IDs in to make it unique, so we can always figure out that we're not adding, when we're adding the same thing twice and when we're not. So that's what we put into the set. Each host only ever manipulates its own entries. We have a little thing that understands, it's basically monitoring the Docker event stream. So when a container starts up or when a container dies, then we can add it to the set and take it out of the set. And we only ever do that on one host. So there's never any problem that someone else made an inconsistent update. As long as the thing is tagged with a host name, you can always do these updates anywhere you like, and we can just merge them across the network. It's not a problem. How do we delete an entry? So adding things to a set is easy. If you took it out the set, you have the problem the merge function it doesn't help you anymore. Somebody else somewhere else in the network could have a copy of the set with that entry still in it, and you merge that copy and it's back in your list. It's gone wrong. So the technique for dealing with that is to erect a tombstone to say that this entry is dead, and so you basically add another entry which tombstones the first one. So that's the kind of trick to get around that problem in CRDTs. How do we do IP address allocation? Probably a bit too expensive to have a set of all the IP addresses in the universe. Even though we're only dealing with IPv4, there's still like billions of them. So we don't do that. We just view the space of IP addresses as a ring, and we split the ring. We put split points into the ring. So if you're on a host that owns part of the ring, you can just use it. If you want to rebalance, move some IP addresses from one machine to another, in an administrative sense, then you just insert a split point into the ring. The details of that are not important. I just want to sort of mention this is the way we address that problem. And if you're interested, all the software is open source. It's on GitHub. You can go to our website, weave.works, and see how we did it. So we implement IP address allocation with the CRDT. It has this property that you can be connected to the Weave network. You can fold your laptop up. Everything else carries on running. You can open your laptop in the coffee house and connect back again. That's exactly what we were aiming for with the CRDTs. Let's take a little sidebar into the subject of gossip. So sending out an update, if something changed, I want other people to know about it, you could send the update to everyone immediately. And that doesn't scale very well. If you have N hosts and they're all talking to N other hosts every time something happens, and particularly if the thing that they're talking about has like N things in it, then you've got an N cubed data problem. Don't do that. Most kind of tools in this space, they adopt what's called a gossip approach. So instead of telling everyone about it, you tell a subset, randomly picked. So it's a randomized algorithm. It kind of fits with the eventual consistency model. So imagine you had 1,000 hosts, then you randomized, your gossip algorithm might pick 10 of them each time at once. So one guy tells 10 others, and then he tells another 10, she tells another 10. The gossip gets around the network. And one of the problems we have to solve, we aim to work in any kind of topology. So this idea of pick N hosts to talk to, if you're on one side of that little thin divide in the middle and you just randomly pick hosts, then you would maybe not talk across the divide very often. So we have extra intelligence in our routing for gossip that says if your topology looks like that, then try and keep both sides of the narrow link up to date. It's another little wrinkle in what we do. Okay, just a few things I wanted to mention at the end. So I said if you delete something, you add a tombstone. So after you added an address and added a tombstone and added an address, your machine's going to fill up. So you time out the tombstones, and that can be a real trick of trying to figure out when is it safe to finally take something out of your data structure. CRDT is not something you can just you download the thing and run it and it's there, because it is your data structure, right? It's something you have to take your problem and think about whether it maps into the properties of a CRDT, and then you can start work with it. So that's kind of unfortunate. It's not something I can just give you the link and you can install it and it runs. And finally, we do have a problem of bootstrapping the IP allocator, because you could get independent machines that think they're in charge separately. So we actually do use Paxos. Don't tell anyone. But we use it exactly once. So we don't really have, we don't worry about the performance problem or the availability problem because you just started the system up, so you should really know about it. So yeah, 3 rules of thumb to leave you with. My basic point, don't force consensus unless you need to, or you don't have to at least. I'm not knocking etcd, console, any of those tools. They're great tools. I'm just saying there's another way to do it, and it gives you certain benefits. If you want to go that way, definitely CRDT is a really key thing to know about. But you do have to take a lot of care when designing these things and think about the ways in which your distributed state is going to move around. Just before if anyone has a question, I just want can we get a show of hands? Who before I started talking, who had heard of Weave? You raise it. Oh, 3/4, 4/5, something like that. Who's tried it? Who's downloaded and installed it? Maybe a third. Well, okay, that's cool. Yeah, everyone else should try it out. And we have multiple products. The Weave Scope one is kind of cute. Draws the diagrams and lets you see what's going on. So take a look at that. Okay, move to questions. Anyone got a question? Yes, we have one in the middle. Are we doing microphones?
Sure, or you can shout.
I can just tell you that you can.
All right, pass it over. You can do this.
It's quite a simple question, actually. Why did you go with Paxos instead of Raft for the IP allocator bootstrap thing?
Why did we use Paxos instead of Raft? Basically because we could use simple Paxos. So if you do like the Greek letters and the funny symbols and you're really into that, there's a thing called multi-Paxos which you kind of have to use if you're doing it for real, for big complex data structure, and that is horrendously complicated, and things like adding nodes to a consensus algorithm is a real nightmare. So we don't do any of that because we only use it once. So we use simple Paxos implemented in 200 lines of Go, and Raft Raft has all those features. Once you got the whole of Raft, it's actually simpler than the whole of Paxos. That's kind of the idea of Raft. So we didn't need all the features, and simple Paxos is simpler than Raft.
Anybody else before we move on?
There's one over here.
Okay.
Do you want to shout out just to save latency?
Yeah.
Is UDP not a good way to broadcast things? Right. Yeah, so the fundamental answer comes in multiple levels. So what you're really talking about is using your network routers and switches and so on to do broadcasting rather than trying to do something in software. And a lot of the time, your network ops people have disabled those features on your network, or at least you will find it very hard to broadcast out of one local segment of the network into another segment of the network. And if you remember the picture I put up, Weave can run on 2 different clouds, right? You can run half your system on Amazon, half your system in Google. You cannot broadcast between Amazon and Google using UDP. You can actually do it using WeaveNet because we run a software network, but I'm not here to plug the product. Yeah, it's one of these things where the fundamental network technology and things like multicast kind of ought to solve that problem, but by and large, the management problem of running those things as an ops problem means that they're not actually available everywhere you want to use them. If they are available in your data center, fantastic. Very efficient, great way to do things. But most people, you go to Amazon, AWS, you cannot run multicast on their network. So, yeah, you have to do it in software. All done?